So let's keep going. We have two sessions left, basically. One is the session on reinforcement learning, and one is the broader sort of what's happening in research and wrap-up. Reinforcement learning is a whole giant field by itself. And so, yeah, this session will be a little bit higher level. I didn't pull in code examples because I tend to be a little bit bigger and longer than the previous stuff. But the idea is hopefully that by the end of this, you'll have a good sense of what reinforcement learning is, if you don't already know, and how it actually ties to deep learning. Right? Why do people talk about these two things together these days? Yeah, and we'll talk about some applications in robotics and games. And I'll give you some pointers if you're interested in pursuing, learning more. There's certainly plenty to learn and lots of things out there to read and look at. So RL in general first. I don't know how much experience you guys have, if any, with the reinforcement learning, but basic problem, right? It can be summarized as learning in some environment where your actions can actually change the environment, right? So rather than a classification where someone just tells me, okay, here's an input, you classify it, and you just get told right or wrong. Here, you're an agent in some environment where over time you have to choose, make certain decisions, and those decisions that you make or actions actually affect the environment, right? So you can imagine something like, a car learning to drive, right? If you're driving down the road and you suddenly decide, you know what, I think right now a great action to take would be to turn the steering wheel left. If that makes your car crash into something, then you're going to have a hard time getting to your destination, right? So, and in particular, or even doesn't make you crash, it means, okay, now you're going left. And so future actions will now should depend on what you just did. So you make some action, you get some change in the environment, and then you can observe, okay, now what's happening in the environment via some kind of observation mechanism. And typically you get reward of some sort, right? So it tells you, okay, that was a good idea, maybe that was not such a good idea. That's the general framework. Lots of applications, right? So games, I make a move. In chess, now I have a different board position. Now you make a move. At some point at the end of the game, I discover that was a good, I win or I lose, which is very concrete reward. Throughout, I might also be able to get some kind of intuition, like, oh, I got one of your pieces. That was a good move, maybe. Buying ads, right? So if you're making an agent to buy Google AdWords, you can think of that as a reinforcement learning problem, right? I make decisions. How do I spend my money on ads? I get feedback. Okay, are people buying my products or services? Whatever I'm advertising, and it also potentially changes prices in the market, et cetera. Trading stocks, same thing. Optimization and control, sort of in supply chain, can also be thought in this way, right? If I decide to store some stuff, in some part of my warehouse, and I can't store future things there. Hiring people, medical treatment, I decided to do this. Here's what happened. You may or may not find out for a long time whether it was a good idea. Lots more examples you can come up with. Okay, so right, in general, the model is, okay, we have the state of the world modeled in some way. We have some sort of actions. We get rewards of some sort. And the goal is to learn to take actions that maximize some function of the reward, right? Either immediate reward or typically long-term reward, often with some kind of discounting. So let's quickly sort of think about what this might look like if you're thinking about stock trading as a reinforcement learning problem. So what's the state? Well, actually, what's any of the three things, right? What's the state or the action or the reward? So state might be the stock price, sure. So yeah, I guess let's make it a simple problem. Let's say we're trading just one stock for now. So right? Actions could be buy, sell, do nothing, and various more complicated things. The state definitely better include your budget, like where am I, and do I own some stock already? Basically, what my inventory is, what my budget is. Okay, what else? Reward is probably reasonably straightforward. Am I making money in some way, right? Profits, whatever you want to call it. State, I think, is interesting for this application, right? Because if you think about it, right, if you're as a person thinking about buying a stock, what are some of the things that you would want to take into account to make a decision? There's a lot, right? There's, I mean, certainly like the price history of this stock, what's going on with related stocks, what's happening with the market overall. That's just the financial indicators. But then there's a whole world on which, in principle, all these financial things are actually based, right? So geopolitical situations and explosions in factories and the latest jobs report and everything else all potentially can be part of the state. So for these complicated problems, you have to figure out, okay, what part of it am I actually going to look at, and how am I going to represent all those things, and which parts am I going to ignore?
How is this different to traditional machine learning? Traditional machine learning, you want to optimize the loss function. What's different between?
Sure. So how is this different from traditional machine learning, where you have a loss function? I think the main difference is that your actions, well, so sometimes you don't actually know what function exactly you're trying to optimize. I guess that can be true in traditional ML as well. Your actions can change the environment, right? So if I buy a lot of stock, the price will change. And again, if I'm making decisions in a sequence, the available actions and certainly the environment in which I'm operating depends on previous decisions that I've made. That's typically that's the main difference. Sometimes it's very, very clear, right? If you're doing robotics, and you're having a robot that's trying to learn to navigate in some environment and achieve some kind of goals, it's clear how you took an action, you decided to go this way, so now you're over there, not over here, and have a different set of possibilities available. Sometimes it's less obvious, and you can think about it kind of either way.
Actually, it's not clear to me how it works. Let's say, like, in this context, like buying stock, let's say I buy stock. On the next thing, let's say the price goes up.
Yep.
So I get a reward for what I did previously, I guess. But then, like maybe later in the future, it will go down. Then, so I guess.
Right. So I think defining reward is also can be non-trivial, right? So in some ways, and again, you can think about general sort of trading and what kind of things people optimize, right? If I buy a stock today and the price goes up tomorrow, should I get a reward or not? Maybe I shouldn't until I actually sell it, right? So I can see, okay, what was my actual revenue? Or maybe I need to represent it as some potential reward. If I'm doing long-term investing, my goal might be, okay, I want stability and sort of slow growth, etc. So yeah, I think this is why we did the exercise. It's not always trivial to model. Right. So why is this hard and why is it different from machine learning? Traditionally, your actions determine the future to some degree, right? If you mess up now, it can be hard to recover. Oftentimes, your observations of the world are noisy and incomplete. And so you don't just get like, here's the image, and now give me the right answer. You have noisy samples. There's this non-independence, which again is not unique to RL, but it's common to RL, where if I'm, well, yeah, basically, the future state depends on the previous state, and if I'm exploring some space, then I'm going to have lots of samples that are sort of relatively close to each other. Often, if I'm playing some game and making decisions, the state of the game changes often relatively slowly compared to how fast you're making decisions. And so, you're going to have a whole bunch of things all like in level 1 as I'm just starting, if I'm trying to play Super Mario Brothers. And then there's this exploitation challenge of not even knowing what all the possible states are in most realistic settings. and sometimes not even knowing what all the possible actions are, right? So, if you're trying to learn how to drive a car around Chicago, you might have to drive around a lot to figure out, okay, here's all the weird things that exist in various places in Chicago, right? Different size intersections, different light configurations, driving underneath the elevated subway, etc. And even more so than other applications, often gathering data is expensive, right? If you have to actually drive a physical car around to gather data on what the environment looks like in different places, that's different than just dealing with sort of software. And again, all of these are somewhat application dependent. All right, so how do people think about this? Basically, there's typically two key elements. There's a policy which says, okay, given where I am, what do I do? Often written as pi, as a function of a state that's encoded in some way. And how do we come up with that policy? Well, typically we think of this quality function that says, given some state and some potential action, how good would that be? And so if I knew the set of all possible actions in the current state, and I knew how good they were going to be, then I would just take the one with the biggest Q value, and that would be my policy. If I don't know that, then that's the goal, right? How do I either learn a policy or learn a Q value? Those are sort of two general approaches. And then there's the final note here. Oftentimes, if I'm trying to maximize reward, I'm going to say, look, I'm going to value immediate reward more than really far off reward. So there's some discount factor, often written as gamma. So what's reward, right? If you're playing a game, you win or lose, that's easy. If there's some kind of points that you're getting, you want to get a high score, that's easy. If you're doing robotics and you're trying to make a robot that walks, if your robot falls over, maybe that's negative reward. It's not always clear what a positive reward is. You could say time, right? How long do I spend without falling over? You could say distance if you're trying to walk, like how far did it get before it fell over? What happened if it partially falls over? And there's other situations where you might not have a clear definition. Timing can vary a lot, right? So if you get rewards frequently, that tends to be easier, because then if I did something and I get immediate feedback, then I know whether it was good or bad. Chess is sort of an interesting example, right? Where I make a whole bunch of moves, and in the end I lose. Which of those moves were good or bad? Not clear. Right, so that's sort of that last problem of, reward credit assignment is what it's called in RL. Like, I did a bunch of different things. Eventually, something happened. Which of those things were really important? Which weren't? States also varies, right? Sometimes I know exactly what state I'm in. So if I'm playing chess, I can see exactly the state of the board. If I'm driving, I kind of know where I am, up to some error. If I'm trading stocks, depending on how all-encompassing you want to define the state, you only have very partial information. Number of states varies. And typically people make this Markov assumption, which is kind of the same thing as we saw actually with our RNNs earlier, that says, I'm going to think of the state as encoding anything that's relevant about history. So given the state, I should know sort of everything that I might want to know to make a decision. Whether or not you actually kind of have all that information is a different question. But this is typically how people model things. Actions, same thing. Simple spaces, right? Do you want to move? Here's a set of valid actions. Go up or down, go left or right, etc. Might be continuous actions, right? Turn the steering wheel this many degrees to the left. Could be simple. Could be a vector, right? Adjust the servos in the robot using this, 18 parameters for the 18 different servos. 19 servos on my slide. Could potentially change over time, and the effective actions may or may not be known and deterministic. So again, if I'm playing tic-tac-toe and I put an X in the top left corner, there's going to be an X in the top left corner. if I'm trying to make an industrial robot and it tries to put some package in some location, sometimes things will fall over and actually end up in a different location. And then potentially there might be multiple agents in this world that are trying to mess with me or trying to help me. So games tends to be adversarial. Driving tends to be, who knows, hopefully just kind of random and mostly cooperative, but sometimes crazy, etc. So let's not go through all of these, but here's another check on whether this all makes sense, right? So maybe one way to ask about this question is, which do you think are simpler to model in RL and sort of easier reinforcement learning problems, and which might be harder, and why?
Yeah, like anything that's like a reward like so far away, one probably is very hard.
So card games might be hard because you don't get a reward until the end of the game. Though in some ways, I could counter that and just saying like, look, the card game lasts a few minutes. And so I can play lots of games pretty quickly.
Oh, can it play with itself, right?
It can play with itself or it can play with someone else. But I'm just saying, compared to something like choose treatment for patient, where I might not know your health outcome, for 10 years. And so that's can be hard because I'm just not getting feedback very frequently. Card games are also interesting in that it's often a partial information, almost always a partial information kind of setting, right? Where I don't actually know the whole state. The whole point why the game is kind of fun is I can't see your cards. And so I have to figure out, okay, what cards might you have? How can I infer what you're doing based on what your actions are, et cetera? But at the same time, the action space is very, very simple, right? I know I have some cards. I know I can play one of them or two of them, whatever the rules are. But there's rules, and you can follow the rules. Whereas, again, in some of the other cases, it's much more vague or much more complicated.
So it stocks is also sure it's very hard, just because there's very little signal.
Trade stocks, right? So partly it's hard because there's lots of noise in the in the market. And I think really, right, I don't know that much about finance, but I know it's much more complicated than buy stock, sell stock, right? There's all these different options of what you can do, and hedge this and buy that and short this, etc.
You can't play a lot of games to do exploit and stocks.
What was that? You can't?
You cannot a lot.
Right. It's also hard to do exploration. At least it's expensive to do exploration.
Well, I mean, you can do it because
But I mean,
you can backtest things.
You could do like stocks depends on market liquidity and stuff like that. You may be able to trade one or two stocks at a particular price. But if you want to trade 1,000 stocks,
right.
and then
it will affect it.
Right. Your actions change the market, so you can't assume that if I know that the stock is going to go up a little bit, I can just buy 1 million of them and make a bunch of money. You have to actually somehow model what the effect of your own orders are going to be, et cetera. So
for RL kinds of applications, one thing you need to think about is, that by doing certain things, you can always get a particular reward. You can get to that particular state in some ways. You can keep on doing it, right? And not have to worry about anything else. And hopefully you will get those local rewards. But then you may be missing out on this other opportunity, which could have gotten you much further along had you explored it and found out there was a better way. Okay? That's kind of the paradigm shift, if you will, wherein, rather than you basically saying, well, what's the best way to go? To climb a mountain, you could potentially just take baby steps, go towards a particular mountain. But if you had gone this other way, there could have been an easier path, and you could have reached your destination much, much sooner.
Yeah. Okay, so that's kind of the big picture for what RL is and why it's interesting and hard sometimes. Let's talk about a couple of different ways people try to actually do it. So one is called Q-learning. As you may guess, you try to learn the Q function. And so the basic idea is, we'll start with just some random Q function. So for each state in action, we say, look, there's some random observe what state you're in, pick an action, see what reward you get, update the Q value to reflect the reward a little bit. So it's sort of you're averaging the old value plus, plus the reward, plus the discounted expected reward of what the next step is going to get you. And alpha basically just says, don't change the rewards too fast. Yeah, so essentially you're saying, look, I'm going to estimate how good this is probably going to be. And it turns out that if you just run this for long enough, which can be very, very, very long indeed, this will converge to give you accurate estimates, right? Because everything starts kind of random, but every time you get a reward, you adjust things to be kind of closer to the right answer. And then as some of the Q values get closer, then next time you reference them, when you're in that state, you update them. Does this make sense? Going a little bit fast.
This one is here. I don't know exactly how it works.
So again,
it would be nice for us to see.
This is basically like a bootstrapping thing, right? That you're basically not.
So you
have this new state, but you also want to kind of have it's basically weighted average.
right. You're doing a weighted average of here's the previous value, which starts out random, but over time hopefully is going to get better, and something, right? So what is this something? The reward I just got, right? So that's something I observed. I just took an action. I got a reward. Maybe it was 0. Maybe it was non-zero. And then what should the Q value be? I guess that's the way to think about this. So ignore this. This is just to like go slower and don't update too fast rule. This is really kind of the value that it should be. It should be the reward I got immediately plus the expected reward I'm going to get going forward, which is discounted. So this is a discounting factor. And how do I know what reward do I expect if I now ended up in this new state? Well, if I had an accurate Q value, I would be done. I would just say, look, give me the best action from the state that I'm in now, right? That's prime. And what's the Q value for that action? That tells me, how good being in the state is, basically.
That's a little because, like, for instance, I'm thinking in terms of stocks again. Yeah, if you know, like, they are out of all actions, like the maximum will be included, right? Like, just by the world.
Maybe, but with some fixed budget, even if you knew exactly what to do, you probably wouldn't be.
But you can do lucky.
I guess think about it, at least to start, think about it in a much simpler setting, right? Think about it in, I don't know, a toy robot trying to get around the maze and find some outlet of the maze, right? So the action is, and you keep starting from the same point and sort of trying different strategies every time. So then the question is, okay, if I do this action, is it getting me closer to the, like how long is it going to take me to get to the output? And so for each state that I'm in, imagine it's a grid. If I go up, maybe that's good. And so then that should have a higher reward, higher value. If I go down, maybe that's less good, so that should have a lower value.
The application I've seen in terms of stock model is in terms of figuring out optimal execution patterns. Okay. So it's kind of a stochastic control kind of a problem where you could potentially say, I'm going to sell 1 million stocks now. Or I can do VWAP. Or I could basically do TWAP, time weighting, volume weighting. Is it a good idea to start small and then go big, close to, my deadline is 4 o'clock trading day. So what are my different options, right? So you do back testing, typically figuring out, like, if I was at a particular time step, what would be the ideal way to get to my ideal state. So that's where you're going to be thinking about best actions. So if I basically do all those actions now versus do those actions later, explore, exploit, buy a little, then sell a little, and then keep on going towards my goal, or keep on just buy, or just say sell. So you'll have to like play around with multiple things to figure out what is ideal, because that ideal thing may not be replicable. You'll have to figure out what may be happening in the scene. It's kind of the same problem with buying ads, right? Do I build all my ability to pay now, or think about what somebody else's ability to pay is to figure out what's the best way to kind of optimize on my work. Any thoughts on bidding in terms of ads?
could be like a, it's kind of an audiobook example.
Yeah, and I mean, again, I think part of the challenge, actually, this is a good, well, I didn't even have all the difficulties here, right? Q-learning is great if you're playing a game, you're running some simulator, you know exactly, there's like a small number of states, you know exactly what state you're in. When you take an action, you know exactly what state you end up in, you get immediate rewards, that you can measure. Then you just do this, simple math, and you run it long enough, and it converges. Sometimes, the number of states is infinite, so it's kind of hard to keep a function, Q of S. Number of actions could be really high. So the dimensionality is a problem. Sometimes you don't know what state you're in, right? So I don't know exactly how many other people are trying to buy the stock right now, or how much demand there is for this particular keyword in ads, et cetera. And also, credit assignment is also related, right? If I'm going to take a lot of actions and only get a reward after 100 steps, one of these updates, right? If after state 100 I get a reward, I'm going to update, the value for state 99, and everything else will still be zeros, or not zeros, random. And then the next time around, when I get to state 99, I'm like, oh, state 99 seemed kind of good, so I'm going to update state 98. And sort of you back this up very, very slowly with sort of exponential discounting, basically. So it takes forever if you have very rare rewards. But there's variants that try to make it better. So here's one example, right, for playing games. If you're, so there was a pretty famous Q-learning with deep learning paper a couple years ago, and a lot of follow-up since then. So look, let's play Atari, right? So play Breakout. The action space is pretty easy, right? I can go left, I can go right, or I can leave the little pattern where it is. The reward is a score, which I also just get back immediately, though I don't necessarily change it immediately after an action. And the state is just, here's all the pixels on the screen. And well, actually, that's not quite that. It's that including plus which way the ball is moving and how fast. Sure, but I mean, I guess, so you can either, you can model this as, an easy way to model this would be if I actually knew where the paddle was and where the ball was and where it was going, and just give me a little matrix for which blocks are still present. What they actually tried to do, and this is where deep learning is going to come in, is say, you know what, I can easily model Breakout that way, but let's try to make something that's more generic. So I'm just going to give you pixels, right? I'll show you the screen, and I'll tell you can move. I'll give you 3 actions, which are going to correspond to left, right, stay, and I'll give you the score, and you have to figure out, given just a bunch of pixels, like what the heck do I do? Because if you can do that, then you can play any other game, right? For for Atari, for example. So that's. But
it has to be some sort of like LSD or something, because like it doesn't know if you just give like an image. I don't know where the ball is going.
Right. So one question is, how do I give you enough information to know what's happening with the ball? What they did, basically, you can give it 2 or more frames of history, and then you can figure it out. So I think they, in the paper, I think they use 4 frames. So they give you like the last 4, maybe skipping some frames, so you can see the motion. Yeah, so I guess we just talked about this. Right, so given the screen and sort of the history of the screen, I need to decide which way to move the controller and whether to push the button. I see scores, and yeah, so that's the policy. And we already mentioned the history thing. That's an important note here. Right, so state space in the all pixel thing is really, really big, right? I'm not going to be able to say, okay, for all possible screens, here's what I should do, because I just can't enumerate them all. Not to mention the fact that history is even bigger. So what did you do instead? Basically, there's sort of a couple of ways you can do this, right? One is to say, look, we're going to approximate this Q function and try to learn a network that, let's take one on the left first. Given a state, right, so a couple of screens, and a potential action, go left, will predict, how good of an idea is this likely to be. And so, basically this will be a standard sort of convolutional network that takes our input pixels plus this one extra input for the action, and spits out a value. And if you could learn this network to do a reasonable job at predicting, then you can try, basically run it for all the possible actions, decide which one gives you the best estimate, and do that. What they actually did was a little bit more clever. Just computationally, it's faster. They just took the state and had the network spit out an estimate of how good all the actions are at the same time. That way, they only have to do one pass through the network to decide which action to take. Note that, of course, to train it, you're only going to get one of those. You only take one action, so you're only going to get feedback in one of them. And so you can only, you basically update the weights to get a higher probability, or higher score rather, for the action that you chose, and the others you just ignore. So yeah, that's basically what they did. So here's a figure from the DeepMind paper. Deep Q-learning, you take your image, you do convolutions. They had whatever, activation function, convolution, activation, convolution, activation. No, I guess 2 convolution layers. A couple of fully connected layers, and then there's however many different, like 18 or 19 possible actions.
Do they have to play the entire game before, like, updating stuff?
I'm trying to remember if I have the training thing here. Yeah, so how do you do this, right? You have your network, so you start the game. Like, okay, so what do? I need to immediately take an action. You pick some random action, and then you see what happens to the score, right? So whenever the score changes, which in some games is very infrequent, in some games happens pretty regularly, you get feedback that says, oh, that was good. Oh, that was good. Oh, that was good. Oh, that was not so good.
So
so there's a couple ways you can do it, right? One is for deciding when to take gradient updates. Every time you can do it, in theory, you could do it every frame, right? You just see, I just took an action, I waited 50 milliseconds, and I see, yeah, so then if it's 0, then you just don't, nothing changes. And you're like, great, there was no error, I didn't get any feedback.
Yeah, but it doesn't propagate, right? Because let's say we're talking about the target game.
Yeah.
Like, the action of moving to the left, your score is actually one people hit.
Exactly. So
you need to propagate that to this action, not to current action, what's happening here.
Right. So what you end up doing is you keep a history of a bunch of actions that you've taken. And when well, no, actually, that's not true, right? So Q-learning, it's stupid, right? Basically, what it's saying is, it's exactly that, right? You're only saying, you're going to learn that, hey, being in the state where the ball is headed toward a brick, at some point, right? You will actually get positive reward because you're about to hit something. And then, the next time around, this thing comes, this happens, you're going to learn, oh, being in the state just before the ball is just about to hit a brick is also good. Because if I'm in that state, then I'm about to be in the state where, I'm about to get points, and then I'm finally going to get points. And then eventually you're going to, sort of back up these values to say, you know what, hitting the ball so that it starts going toward the bricks is good, because eventually I'm going to be in other states that I have high value. Right? So and this is why it takes forever. In fact, that's on my next slide, to train. Because it's not really doing any planning. It's not saying oh, I understand there are objects and they're moving, and so once it's moving, it's going to get there. It's just learning that, hey, when I see a screen that looks like this with the ball moving in this direction, I can predict what's going to happen next. And if that next step, I've seen before and I think is good, then it'll do well. The other trick that you end up having to do actually is, rather than training sort of really live as you're going, what you do is you play with the same policy for a while, and then you scramble up a bunch of the state transitions from different games and different times in the games, and train on that. That way, you're kind of getting a more random sample of the policy space. And so intuition is like, if you're learning to drive a car, if you're feeding my experience sequentially, then you're going to like learn to drive to the left really well while I'm turning to the left. And as I start turning to the right, I'm going to forget all about how to turn to the left and start learning how to drive to the right. Problem in networks. So you have to randomize all the actions to deal with that. But it works, is the crazy part, right? So one of the things you have to do is also occasionally take an action that doesn't seem like a good idea. This is what Sri was talking about earlier. It's a standard sort of reinforcement learning thing where, right, you're trying to explore and discover new state spaces that may actually turn out to be good. So that's another, there's various ways to do that. The simplest one is just having some fixed probability. Sometimes you reduce it over time. Yeah, so I guess I just said that. If the environment can change over time, you want to make sure to keep exploring. If the environment is fixed, then over time you can stop exploring and sort of exploit the knowledge that you've gotten. If you're in an environment where you can lose all your money or crash your car, it can be challenging because you don't want to randomly decide, you know what, my self-driving car is trying to learn how to drive. Right now, I'm randomly deciding to try a new action, so I'm going to crash into the wall or drive off a cliff. So, and also sometimes you're worried about, how can I test things in a safe way? If you have a simulator, like a game, it's great, right? You can crash 100,000 times and lose the game 100,000 times, and who cares? It just costs you some CPU cycles. GPU cycles, probably. Okay, so there's a different way that you can try to do RL. Ultimately you're solving the same problem, but rather than running these Q values and saying, how good is this situation? I'm just going to say, forget that. Just tell me what to do, right? So feed the network. Here's Pong. Like, here's a bunch of pixels, what the screen looks like, again, with history, so you know if there's motion, and just train the network from that to probability of particular actions. So Pong is easy because there's only 2 actions, up or down. We do that. And again, if this network is trained, then we're happy, right? We're going to choose the right action, and we'll play the game well. So how do we do this? And the trick is, basically, it's kind of like supervised learning in the sense that if I knew that up was a good action, I could just do what we've been doing this whole time, right? I just backpropagate that, yes, that was good, increase the probability of up. If it wasn't a good action, then decrease. What we're going to do is pretend, right? So we're going to play a bunch of games with some fixed policy. So we'll start with a random policy, which is to say, a randomly initialized network in this case. And so it chooses a bunch of actions, however it does. And in the end, you get some feedback, right? So you win the game, or you win that round, or you don't. And then you just start again, you try again. And then we're going to say, you know what? I don't really know which of these actions was good or bad, but somehow in the first game, some of them must have been good. So we're just going to pretend they were all good. I guess, yeah, I forgot to mention, right? As we're going, we're going to basically keep track of what the network was at each of those times, so that if I do decide, you know what, this up over here, the top left, was a good action, I'll know how to update the gradients, backpropagate the gradients, so that I can increase the probability of that action, and vice versa. And then, yeah, so that's what I just said. I forgot that I had this animated. When we lose, we will just reduce the probability of all the actions in the sequence, right? So apply the gradient updates so that those probabilities are lower. And if we win, we increase the probability of all the actions in the sequence. And it turns out that if you repeat many, many, many times, this actually works, right? Because somehow, something about what you did presumably was good when you won. And so you're going to be a little bit more likely to do those actions next time, and a little bit less likely to do the actions that were bad. It's kind of silly because you're making all these updates that are sort of counterintuitive or wrong, at least random, and maybe worse. But on net, there's kind of a drift in the right direction. And so I think I can actually play this. No, I clearly cannot play this. Go here. So here's a video. Again, Karpathy has a little demo on reinforcement learning, playing Pong. So here's his deep neural network-based Pong player. Which one do you think? Gotta be the right one, right? Going crazy. It's like, and it's interesting, right? Because you can see, like, when it doesn't matter, it's pretty much random. It's just flailing around. When it does matter, it actually seems to do a pretty good job. Like, oh, I need to move toward the ball. But once the ball is already on its way to the other side, it's like, I'm just going to flail. But it learns after some, pretty large number of trials to do a pretty good job and win fairly consistently.
You're saying
Right. So this just learned the policy. And again, of course, you can figure out, well, you could try to figure out the Q function.
It also depends on your pedal speed, right? If your pedal speed is infinitely fast, you will never lose.
Sure, but I mean, this is playing a fixed game, right? So both sides have the same limitations on how fast they can move.
Okay, but you can see that the green one actually moves much faster than the yellow one.
I think the yellow one could go faster if whatever AI is controlling it was smarter. I mean, it also could be that he actually made a cheating version of Pong that's easier for the green player, but the general approach is the same, right? Like, and you can see that actually this is a good example if you want to look at code. He has a tiny version of like 100 lines that does this whole game.
Oh, okay. So you have
I mean, there's a reference right there. It's Karpathy's blog from last, whatever it was, May. Actually, yeah, exactly a year ago, he published this blog post. Anyway, we can stop watching that now. But yeah, so policy gradients actually works. Shown here, actual size. Again, for, wait, how do I stop this? Okay. Build a game AI, lovely. Okay. Right, so some of the things that help this is you have a Pong simulator, and you can play as many games as you like for free. In general, sort of to your point, right? Here, he learned to be a particular opponent, whatever was built into Pong. If you were playing against someone else who was smarter or did some other strategy, that might not work. So you have to actually learn to play against other opponents. Yeah, if you're trying to do financial trading, it's maybe harder to get a good model of what's going to happen if you make certain decisions. If you're driving around or doing robotics, I think we'll have a picture later. Google has some cool blog posts like, look, we built a little robot army of a bunch of hand robots running to grab things, and they're all getting training data. But it's expensive, right? Then you actually need real hardware. But yeah, so if you have a simulator, that helps a lot. Just a quick plug for OpenAI. This is a company that people started last year, nonprofit actually, in the Bay Area, to try to help make AI more accessible to random people around the world, and not just the province of Facebook and Google and IBM and so on. One of the first things they did was actually build this thing called OpenAI Gym, which is a reinforcement learning environment where you can play a whole bunch of games and simulators using a very generic interface. And so hopefully at some point people will have algorithms that work well sort of across a whole variety of different environments, right? Playing games, robotic simulators of various difficulties, et cetera. So if you want to play with simulators in RL, this is a great place to go.
And Universe too. That really extends the right. It's like it's gonna have GTA 5 now.
Yeah.
That you can play with.
It's pretty interesting. And there's actually a lot of systems work to get this to work well, sort of fast enough, et cetera.
It's also one contest. This is AI.org.
Yeah.
Where you can use different data sets. There's like a learn to walk, learn to run.
Yeah, so there are others. DeepMind actually has one as well. I don't know if CrowdAI is that or is it a third one. Okay. If you get into RL, you'll learn about more of these. Yeah, it's pretty cool. So let's talk about robotics briefly. Well, this is kind of just a fun demo, so let's quickly look at it. Right, here's another Google robotics thing. So using vision, wait, why is this? There it goes. Okay, right. Traditionally, for robotics, someone would sit down and try to write down the rules of like, here's how you grab things. What they're doing here instead is saying, you know what, we're just going to learn from visual input and reinforcement learning on the actual robot controls. So I'll show you the architecture on the next slide for how they did this. But basically, there's convolutional networks trying to look at this and make sense of it, saying, look, are we about to grab this or not? So there's a prediction of, are we going to have a successful grasp? And then there's a learning algorithm for, if it says yes, then you just keep going. And if it says no, then you, what's the word? Basically, you back up and try again. And so over time, it actually learns to pick up objects of different shapes. And so, as you watch these like hand grasping videos, it starts to notice like, oh, I like to align things so that I can actually grab them with my grippers appropriately, etc. And I don't know if this is an accident or not, right? But often you would start with something like this, where you teach it how to pick up one object, and then you put in two objects, and you put in things all on top of each other to kind of make things progressively harder. Yeah, it's funny. One of my friends did a PhD in robotics and grasping like 10 years ago. And, her whole like 6-year program, in the end, she's like, look, I have this robot that can pick up a drill and, do something with it. Very much more hand-coded. Now you're like, look, if you have a robot and a camera and enough time, just leave it to figure it out. So that's cool. Where it happened. Yeah, so state action reward in this application. You have to participate. Otherwise, you won't learn anything. Happens. So what's the state in action in the robotics thing that we just saw?
State is just like current. I guess in this case, it's just like an image of arm.
Where's the arm? Right? Where's the robot arms? And then where are the objects in the bucket where you're doing stuff? But really, as far as the algorithm is concerned, you're right? It's really just the input from the camera and whatever else it knows about the arm state. Probably kind of what the positions are, etc. So the actions are to decide how to move the arm, and the reward is ultimately only when you finally pick up the object. You get to like, okay, yes, I succeeded, or no, I didn't. I'm actually not even sure how they compute that. You could try to do it from the camera as well, or you can maybe have sensors that say, okay, yes, I'm up in the air and I'm holding something. If you have a weight sensor. Yeah, I guess I had the same question on here. So how do they do this? They make a network that's not just looking at the visual input, but actually saying, given this input and a potential thing that I could do, how likely am I to succeed? And so then you can just try a bunch of different motor commands and with the current input. And if any of them give you a high probability of grasp, then do that. And if none of them do, then back up.
So that proposed motor command does not go to CMM, correct? It's an merge layer.
I think, yeah, we'll have the architecture on the next one. It merges after the convolutional layers. Well, I guess we can just go here. Right, so here's our complicated picture where now we actually understand what all of the pieces mean. Right, so we have two images. They didn't do a good job with the pictures. One of them basically is the image before the robot arm got in the way. So you can kind of see the whole the whole picture. The other one is the current state where you might have a robot arm blocking some of the vision. So it's kind of like you might remember where things were, even if your arm is blocking blocking your view of the thing you're trying to pick up. So 2 inputs, a bunch of convolutional layers with max pooling, repeated 5 times or something. And then after that, you feed in the motor command, which is like a 64, I think, dimensional vector. And then a bunch more layers. I guess still convolutional layers, actually.
Yeah, that's not clear, right?
So you can look at the picture, the paper. I forget the exact details, but basically, spatial tiling. Yeah. So basically, they make it look like an image, just so they can use the same convolutional structure. I don't know why they do that, actually. I don't remember. But then in the end, right, you have fully connected layers, and you get a probability.
But I don't, maybe I missed it. Why?
So one image is what the bucket looked like before you started your motion, when you can see the whole thing. The other image actually shows you where the robot arm is now. So imagine, right, that I have this bucket, and now I'm trying to pick up something. I can't actually see through the robot arm, right? And so since I can't see what's under, you could have more cameras, but this is just kind of like memory, right? This is what I saw before I started, and this is now the same picture, except there's an arm in the way, which is useful when I can see where the arm is, but it's not useful because I can't see what's underneath. And so if I'm trying to pick up those glasses and I can't even see the glasses, without this input, it's going to be harder to decide, like, am I actually about to succeed or not? So it's just a way to simulate kind of memory, basically. Yeah, so again, I forget exactly how they combine these things. There's a reference on the slides. The other cool thing they did here is actually they did this with 14 different robots. This is the robot army, all trying this simultaneously and feeding gradient updates to a single model. I forget, synchronously, asynchronously, or something. So they tried, 800,000 times to train this model, and in the end, it actually worked pretty well.
That's Spark version.
Yeah, maybe. They have their own choice at Google, but yeah. Okay, so self-driving cars is even more complicated. So I just wanted to sort of think about it as an application at a slightly higher level, right? So we have this car. It has a bunch of sensors. It's trying to get me home without crashing into anyone. So again, what sort of state, action, reward?
State, again, I guess, is an image or set of images, however many.
State is where I am and sort of what's going on with my sensors, right? So whether it's visual sensors or laser rangefinders, or whatever else you have, audio, etc. Maybe collision sensors. Maybe I just hit something. So that's the state.
Maybe also current state of whatever speed.
Right. That's a good point, right?
You can probably do it from images, but still.
Kind of like the. No, I mean that would be crazy, right? Kind of like for Pong, you need to actually know what's happening with the car. So what's my velocity? What's the angle? Which way are the wheels facing? Potentially, ideally, hopefully, you also have in the state things like, what do I think the current road conditions are? Is it icy or dry or wet or whatever? Okay, so action.
Left, right, brake.
Relatively straightforward, right? There's a few directions of freedom, right? So there's turn the steering wheel this quickly to this side or not. Adjust, apply this much acceleration or brake. Hopefully not both. Shift gears potentially, maybe probably not actually. That's probably left to the car to figure out in some other system. And reward is something like making progress toward where you're trying to go, haven't crashed yet, haven't run any bicycles off the road, etc. So where my neural networks fit into this, right? I found this slide from a CMU research paper. Like, look, here's a bunch of different models that you'd need to put together to make this all work, right? You have some model of the world, where you're trying to go. You have a whole perception model, a bunch of different modalities. You go from that to some model of, okay, so what's happening, right? Where's my vehicle? Where am I going on a local scale? What's happening on the road around me? Are there obstacles? Are they moving? Are they not moving? What did the user actually tell me to do? Park the car, go home, run that jerk off the road. Hopefully we don't have that, but someone might add it as a post-market edition. It's terrifying. And at some point you have to decide what to do, etc. Right? Some commands to the car, and then it actually goes and drives. So some of these things might be a great fit for neural networks. Others maybe not so much. Yeah, so I think I actually have this here, right? Perception seems like a great place to do neural networks. Potentially, the motion planning thing could also be a network, right? That sort of synthesizes all these things. But in general, this is also Andrew Ng, I think, had a good point, right? Where researchers might actually say, you know what, let's just do this end-to-end as one giant network that solves the whole problem. But today, that's still not what you'd actually do, typically, right? You can't debug that very well, and you can't give any real guarantees that it's going to do the right thing, right? It might have done the right thing in training, but it's hard to know. So what people actually do is still have a more traditional kind of planning algorithm where you can prove theorems about it and guarantee certain kinds of behavior, or at least understand why it made certain decisions, right? So you would say, look, I'm going to build a map of the world that's sort of more abstract than just pixels. Yeah, and then I could say, okay, maybe the mistake was the perception was wrong. I didn't see this bicycle. Or maybe the mistake was, I thought I could get in front of the bicycle before it got to where it was going, and it accelerated faster than I thought it was possible, or whatever else. But these real-world systems for a complicated problem tend to be not just the neural network, but a bunch of other pieces as well. Okay, so one more example, which we already briefly talked about yesterday, right? In this case, games with an opponent, right? But in general, environments where there's people who are trying to mess with you. And so you have to actually react to them. So AlphaGo, that's sort of the most hyped, at least recent example. And I think also probably the most impressive, right? Go was a game that, well, it's very, very simple to describe, right? Just put your stones on the board and surround other people's stones. And 10 years ago, or less than 10 years ago, when we were teaching, I was teaching machine learning, we were talking about game playing. Like, look, people figured out how to win chess, people figured out how to win backgammon, etc. Go is incredibly hard, and we're going to take forever to figure out how to solve it because there's so many moves that are possible. And there's really no structure. Like for chess, a lot of what helped actually IBM, I guess, again, win chess was that people could describe what a good position looks like in terms of, actually a lot of in terms of the different pieces, right? You say, look, if you take the person's queen, then that's great, and if you take their knight, that's less good but still useful, etc. Go, all the pieces are the same, right? It's just a bunch of stones. So you really have to do kind of pattern recognition and figure out, okay, given this arrangement, is this good or bad? And there are several hundred moves possible typically at most game positions. So the branching factor is really high. If you try to look ahead many moves, the number of positions you have to consider is huge. And yet, now people can play better than the world. Fine, I think we've done enough of these, right? So whose turn it is, plus the board position, is the state. Different in that, you know what you're going to do, but then your opponent is going to try to react sort of adversarially, right? They're going to try to do the thing that's worst for you. So there's this notion of game trees that's important to understand for game playing, right? It basically says at each point, like, what are the possible moves? And then for each of those points, what's my opponent's possible moves, and so on. And you can actually then go back from the end and figure out, as long as I make the best move at each step, can I actually win the game? Right? So there's sort of, if I go this way, then I can win. regardless of what my opponent does after this point. If I go this way, then I can at least draw. If I go this way, I'm going to lose, assuming my opponent plays optimally. So you have this notion of a game tree. For Go, it's incredibly, incredibly huge. And yeah, I guess we talked about that.
What do you think about AlphaGo being retired?
What?
AlphaGo is being retired.
Oh, I didn't hear that.
Yeah, that's after the 3 game, then I don't think that's going to be retired.
Okay, I mean, that sort of makes sense. Let's come back to that in a few minutes once we talk about how it works. Right, so the approach here is going to actually try to combine the two things we already saw, right? We're going to learn a way to say, how good is this action from the state? So that's a Q function. And we're also going to learn a network that's just going to say, what should I do? A policy network. And then, roughly speaking, you just do a weighted sum where you figure out what weight you should use. So the question is, how do we do this, right? And what they did is they took 100,000 human expert games that they had data on and said, let's try to learn a policy, right? Basically predict what move the expert was going to make given a board position. That gives you a policy. And given that, you can then play the thing against itself and keep using that policy and learn the value network, right? So the value network says, how good is this position? And how good would a particular move be? Well, to simulate that, you can basically just try that move and, assuming, say, look, if both of us are going to use the same policy and I try this move, let me just run the game to the end after this move using the policy, which we think is reasonably good, and see what happens. If I win, then good. If I don't win, not so good. Because the policy is randomized, you actually do that a bunch of times, right? So you might do that 500 times and say, OK, if I tried this 500 times using our policy and selecting actions according to the distribution that the policy gives me, I won 80% of the time. So maybe this is a good move. And so then over time, you keep adjusting those two networks. And the networks themselves are shown over there. They're basically, simple convolutional networks with this extra input of, where am I putting the stone for the which one? For the policy? No, for the value network. And the policy network just gives you the output that's like a probability distribution over all the positions on the board. Again, there's more details, obviously, in their paper. But the crazy thing is, it actually works. One other, I guess, trick that was interesting, there's a correlation thing, right? So credit assignment, again, this rears its ugly head, where you play this game, you make a bunch of moves, in the end, you win. Which of those moves should you reinforce? If you reinforce all of them, then that is sort of the basic policy gradient thing, but that's really, really noisy. So they cheat. They say, you know what? I'm just going to pick one move from the whole game, and I'm only going to look at that move and reinforce that move if you won, and de-reinforce it, de-emphasize that move if you lost. And if you Google and have lots of data centers, it works pretty well.
Question: why do you need the value? Like basically function? If you have a policy, then what's the point?
The point. So if you had an optimal policy, you wouldn't need it. But the point is,
here, let's say, you said that they were
right. But basically, the point is, if combining the two ended up giving you better performance, right? So both, if you use just the value network and if you use just the policy network, I think both got you to roughly expert level performance. But if you combine them in a clever way, actually not even that clever, then it got so big that they're going to retire it, I guess. I think if you think about it a little bit more, right? I think the policy network gives you that pattern recognition piece. Maybe that's the way to think about it, right? It says, look, I think just at a glance, right? An expert in Go looks at this board and within seconds could tell you, like, you know what? I think I'm going to go here. But they don't. Then they pause and they think about it for a while and they say, okay, so if I go here, what's going to happen? And then they might change their mind, like, actually, that was a terrible move, right? So that's the same thing you're going to do here. You're going to say, look, I have some opinion on what I should do just looking at this board. But then I'm actually going to go and simulate 500 different games based on making different possible moves using this value function, and see which ones of those work well, right? So basically, the policy network gives you some sense of what seems to be a good idea, and then you can actually explore that using tree search to get a better sense of, is it actually a good idea? And so if you get into weird positions where your policy isn't very good, you might still be able to back out like, oh, okay, I should do something different. So I think that's a good way to think about it. And again, more details in various talks and papers. Yeah, I just said that. Fine. So yeah, one against Lee Sedol, who was really good last year. It just beat the world champion pretty handily a few weeks ago. It really is doing something, that you might call intelligent, right? Previous Go programs would kind of, be copying stuff that they saw in all these expert games that were trained on. Here, it was really coming up with things that people were like, look, here's an expert. Like one expert says, right? I would have slapped a student for playing this strategy. And there was a moment in the Lee Sedol match last year where it was like, it bids a move that, people have always said, like, do not do this. This is a terrible, terrible idea. And then, 2 hours later, like, oh, crap, that was brilliant. So people are learning from, well, I guess we're learning from AlphaGo if they're going to turn it off. I'm sure someone else will rebuild it at this point. Yeah, so, right, we're done, right? There was all this hype, like, AI is solved. It's not solved. We have a simulator. We can describe the game incompletely. We can play 30 million games. It's not generalizable to anything else, like the actual model, right? The approaches, of course, is. That's why they've spent all this time on it. But yeah, still lots to do. I guess one other thing I should mention for games that's happened last fall-ish, I guess. Poker is also now mostly solved. For a long time, people were trying to sort of solve smaller versions. Now there's AIs that can actually beat the best human players in poker, which is interesting because that's not a complete information game, right? You actually don't know what cards people have. People can bluff, and so it's harder in that sense.
I think the goal at least is I mean, okay, fine, they did it, but the goal itself, like it's you can give like an advantage to the person, and then you won't be able to beat it, I'm sure. If you give like
Yeah, sure. I mean, I think for a long time, right, it was the other way. It was like, okay, how many stones am I going to give the AI to go first before it can actually be competitive? Potentially, yeah. I mean, I think for Google, maybe not, because they're like, look, we figured this out. We have lots of people who are paying lots of money. They can go work on other problems now.
So for poker, it was the University of British Columbia researchers.
That's one. I think there's also
They have like
Thomas Sandholm's group.
Deep stack. It's a good paper to go through on their approach, called the deep stack approach. It's also on Science Mag. More of a English word.
Yeah, so lots of stuff out there on RL. I picked just a couple of things to throw in here. If you want to know more, by all means, ask me. But the Kripathi blog I already mentioned is a great sort of fairly brief explanation. There's a standard textbook that actually has a new edition coming out this year, and a couple of good online courses, and so on.
Free copy of the book available online.
No, okay, I think I have it from send it to me. Yeah, reinforcement learning is interesting. It's getting to the point where it's actually being useful. I'm actually talking to a company about potentially working there in Berkeley that's doing RL for like industrial optimization and automation. And they have customers that are trying to actually deploy this stuff. So in that sense, it's interesting. On the other hand, there's still a lot of work to do, which is, I guess, a good segue to our next session and last session.